video classification example in a minute. Yeah, so this we have already there. So yeah, so this example basically talks of a CNN RNN architecture, and this basically is trying to train a video classifier with transfer learning, and it uses a recurrent neural network model, and it uses UCF 101 dataset. So this demonstration actually gives us the video classification. It's an important use case, and this particular UCF101 dataset consists of different actions, right? It has got cricket shot, punching, biking, okay? And this particular data set is generally used to build action recognizers, right? Which are an application of video classification. So this is the first step wherein you are trying to set up your environment, right? And then this is where you collect in the data, right? Or the data set UCF101. Then you basically set up your environment wherein you are using CV2, pandas, matplotlib, tensorflow, okay, keras, and all of that. Then you define the hyperparameters. What is the image size? What's the batch size? What is the epoch, right? And what is the maximum sequence length and number of features which you are trying to do. Then you have this data preparation, wherein how many videos are being used for training, how many videos are being used for testing, right? So you are trying to actually use this for training purpose and testing purpose, and then you basically are trying to do, okay, action recognition. In a sense, you are trying to actually do action recognition with TF hub. So this basic idea is that you are trying to generate a sequence model, right? So you are trying to load in the video. Okay, you are trying to load in the video. What is the frame you are trying to use? Okay, and then you are going to actually crop the frame, right, for getting the center, and then trying to understand the region of interest. And then once you are able to extract, right, all these frames, so you are trying to actually do to get the region of interest, okay, which basically gives you the action recognition. So obviously in a frame, in a static frame, there will be some region of interest, right? And that region of interest you need to actually crop, okay? And then each of these frames, okay, could be or should be actually used, okay, by a pre-trained network, okay, to extract certain meaningful features, right, from these frames. So now what effectively happens is you have found out the region of interest in the frames, and out of these region of interest or these portions of your frames, you need to actually extract meaningful information, right? So effectively you are trying to develop a feature extractor. Okay, now when you talk of a feature extractor, the idea is that you are trying to actually get those features which are more important, right, to actually generalize for various videos which you are going to get input for, or you are going to get those videos as input, right? Otherwise a question basically is or might be asked that when you are trying to do a classification and you are trying to use CNN and RNN architecture Why is that you are going to again extract features when CNN and RNN is actually capable of doing it on its own? Okay, so the idea here is that the features are extracted, or features might be extracted, but which are the specific features of our own interest, okay, is something which we need to actually boil down to from lot of features which this type of a network would have given us, right? So we are trying to develop a feature extractor here, right? Okay, and here we are using inception v3, right, for that purpose. So now if you want to see the source and all of this is available in this. Now you have extracted the features, or you have built the feature extractor. Now the labels for each of these videos are strings, and when you say a neural network, or for that matter a deep neural network, it's not going to understand the string values. So you are supposed to convert it into some form, okay, which is basically to be used by a neural network model. So you are going to convert it into some numerical form, okay, and then there is something wherein we use lookup, okay, which basically is a layer which encodes the class labels as integers. So there has to be a encoding done for each of these classes as integers, right? So this is what is done here. Okay, so if you see the label processor, it's going to give us the labels like cricket shot, playing cello, punch, shaving beard, tennis swing. So these are from that particular data set, right? So we are talking of video classification, right? So now once you actually see all this, so what have we done till now? We have actually done these steps wherein we have defined our hyperparameters, we have prepared in the data, okay, uh, which needs to be used, okay, and then we have tried to find out, okay, which are the actions which we need to actually do things, and then uh, we have to basically build a feature extractor, okay, and then we can basically link each of these class of labels to each of these videos, right? And then you are going to prepare all the videos for each of these videos, you are going to actually do all of this, okay, and then if you see the frame features in the training set is this, and frame masks in the training set is this. Now this we have already executed because it will take time, right? And then the sequence model is basically to feed this data to a sequence model, okay, of recurrent layers, okay. So what basically is being done here is you are going to understand, right, why these mask models are required, right? And then you basically try to run these experiments, train it, okay, for each of these epochs, which we have already done. And then once this model is trained, okay, now this particular thing is basically is something like a sequence model with so many trainable parameters, right? And then using this UCF101 data set, and then you basically can use this for inferencing, okay. So the idea is this, that if you run this particular thing, okay, it will randomly take certain images and then do the prediction. For example, this is the video path. What is it doing? It is classifying it as playing a cello 47.79%. It is not surely related to tennis swing, but it is basically trying to give it that particular percentage, right? And then you have cricket shot and punch with respective values. So the basic idea is you need to train it more, right? We trained it with this data set with certain specific number of epochs just to show you like how fast we can do this. Okay, otherwise you can do it for various settings of hyperparameters, then try to do it. We'll try to see this again. It will randomly choose certain videos and see here. This is trying to detect that it is 27.76% as shaving beard, and tennis swing it gives me as 15.84%. So this effectively is a wrong classification, right? So it is not necessary that every classification should be correct because of your training parameters, training values, training epochs, and all of that. You understand that, right? So that is how it is. So let us try to see one or two more videos, and then we will see, okay, of what. Yes. So this is randomly taking pictures, okay, which are not used for training, and then this is how it's going to do this, right? So what effectively is happening here is these video classifications are not correct. Okay, some of them. Let us try to see one or two more. Let us try to understand like what is the accuracy. See here, it's such a easy thing, right? But still it is giving me shaving beard, right? So yes, so basically to remove all of this, right? To remove all of this, there is a concept, or there is this particular approach, right, which is called as inflated 3D CNN usage, right? Now what is basically inflated 3D CNN approach for action recognition is that it also does the same thing, and you can use the Kinet data set, right, which will improve, right, your recognition capability. So what is the difference here? The input again is a video. So the idea is it's a 3D input with a two-dimensional frame with time as the third dimension. Okay, so technically speaking, it's not a 3D model, but it is considered to be a three-dimensional input. It is considered to be a three-dimensional input, okay, as a two-dimensional uh, image frame, right, and time as the third dimension. So in this particular example, uh, we have tried to actually see, right, that these people have used a CNN with two strides or stride 2, after which you have a max pooling layer and multiple inception modules, right? So this is how it is. So in the previous thing, what I have done is I had actually run it before, but now what I'm going to do is I'm going to run it so that so let me just run in the collab thing. 1 minute, give me some time. Yes. So okay, let me just close that session, the previous one. Okay. So in this case, this is basically a solution which was at just the first rank in CVPR 2017 Sherrod's challenge, right? So Okay, so once we are able to install the various modules in our environment, we'll just try to understand and import the various necessary modules. And again, here we are using UCF 101, and then yeah, again the same thing. We are trying to open the video file using CV2 and then crop the center square frame and then trying to load everything, right? And then for each of these videos, we are trying to get the Kinet, right? Cameras labels. And then, so what is the list of videos in the data set, right? All of this videos in the initial this thing. And then it's trying to show you certain things wherein let us try to miss this. Okay, so this sample video which you choose will give you the probabilities, right? It's not displaying, but it will give you the probabilities. And then you can basically try to download certain videos, okay? Trying to understand. And then, yes. So if you see this, this basically is trying to give you a prediction, which is about 96.85%. Okay. Now the idea here is that you have done almost the same thing, but then you have tried to actually link, okay, the Kinet label, right, with basically trying to use the Kinet data set, okay, along with the UCF 101 and HMD basically data sets for fine tuning the models. Okay, and now these basic models which we are talking of a 3D convnet. Okay, if you go to the 3D convnet model, okay, uh, these are pre-trained models which are available to us. So 3D convnet model basically are available to us. And then yeah, so that is what basically is done in this particular thing. I'm not going into the technical details of 3D connet and all. You can basically refer the various links which are there here, and then uh, this thing which can happen, right? So now You can predict anything, you can work on this in your leisure time, and you can work basically on this. We have shared the links on our slides as well. Yeah. So let me just show you some other demos. 1 minute, give me a sec. So the idea is that this is a very simple program which we have been doing, like everybody does it. But the idea is just to show you, right, how basically you can further automate it, right, which we will be doing it in the next class with the deep stream, right. So the idea was how standard applications like this could be improved, right, using deep stream and GPU computing is what we are going to show you in the next class. So, but we'll show you how this is in the standard procedure done, right? So we have this width and height. So trying to understand that, and then trying to basically use mouse clicks to basically find out the areas which you're going to select. So we'll show you that, and uh, then we'll see how this car parking thing works, right? So we'll try to show you this. Uh, yes. So if you see this, 1 minute. So this is, it's not drawing. Yeah. So this is how actually you are going to draw it. Okay. Yeah. So this is how you are actually going to draw it, and then now you can see like this we have put in and drawn. Okay, for majority of this, trying to understand this, and then trying to, you can add in, go on adding more areas and something like that. That should not be a problem. So this is the basic idea. And now if you see, and we start the next step of processing. Yes. So if you can see here, it's actually going to show us the free slots, the count of number of occupied slots, and how basically the frames are getting processed. Okay, and then thresholds are getting checked, right? So this is a standard computer vision application. Okay, which might run on a GPU, which might not run on a GPU. So this is a standard application wherein you are trying to detect the free slots, okay, based on the features available using certain techniques of thresholding. These are not very standard, in the sense it's a standard technique, but it does not use any deep neural network type of approach, right? So how are we going to change this application, okay, to a real-time smart city application using something which is called as deep stream, which is what we are going to discuss in the next session, right? So I hope you understand the context with which this is told today, so that we can actually go into the details of certain specific applications which would be developed using things like deep stream, okay, which is a very good set of libraries, right, which could be used for developing video analytics applications, right? So I suppose I'm done.